Recording's rolling. It is Thursday, April 16th. We're going to do the Kahoot today on circuits, which would be a pretty good review for this quiz tomorrow. We've definitely covered all the content. Now, once you guys got first this lab finish two from yesterday, go recap some of these things with you guys too. Before I do that, you guys have to use that the school board voted to end the school year a week early. So last day's school is now May 22nd. It's like right there. And so some assignments here, some assignments. This page here, you guys remember all these circuits and these four trick-off tables. Right, so I know I covered all the trick-off tables with you guys, a lot of these circuits. Some of you guys have turned in this page already, and if you haven't, then you can turn it tomorrow. It's all right. Although it might be pretty good at studying anyway, because then we have some quiz questions that could be good. And then yesterday, you guys did this resistivity of DOLAB. You guys had these plated cylinders and multimeters, and you're trying to figure out what's the resistivity of Play-Doh, like sort of how conductive is it, all that. And you could get data from that table. Now, if you took length over cross-sectional area, you could get different values. And then the resistance you could calculate from Ohm's law. Right? You guys remember Ohm's law? V equals IR. Okay. And ideally, what you should get is these points lining up in a straight line. And the slope represents the resistivity. Okay. So that could be the graphical version of the answer. Okay. So something like that. All right. And a couple of guys turned this in yesterday already. If you haven't been, turn in. Good points up for you. All right. So you guys ready for Kahoot? Yep.
We got yesterday, so I was like,
all right. Pin is on the board, so you can still sign in. All right, here we go. Circuits.
oh yeah, that's.
In order to form an electric circuit, you need to have all the above. Nice. Right. So definitely a power source, right? Like a battery could be the voltage source that could work, the source of energy. Right. Ideally a resistor, because if you don't have any kind of resistance, then you just create a short circuit. Right? That's like if you attach a paper clip to the lead to the battery, it'll make it really hot, right? And it'll short the battery. Right? Also complete path. Okay, so did you guys notice when you're wiring up all your circuits, if you just went from the anode of the battery to the whatever, like a light, it would never light the light, right? You had to have a complete path that connected to the other terminal of the battery. All right, we got points on the board. Oh yeah, win it. In order for current to flow, you must have a closed path. Right? If it's closed, then the current can flow. If you open the switch, then that would turn it off. Ooh. All right, so closed, the current can flow. All right. There you go. Electrical resistance is measured in ohms. Oh, guys, let's go over all these. What does joules measure? Energy. Hey, guys, what about this? What if you buy something off the shelf at the grocery store and it has so many food calories? Are calories convertible to joules? Yeah, I think it's like a factor of like 4,184 or something like that. Okay. But it's a direct conversion because those are different ways to measure energy. Yeah, energy. What does volts measure? Yeah, voltage or potential difference. If you say either voltage or potential difference, that's okay. What does amperes measure? Oh, electrical current. Yeah, electrical current. And then ohms, of course, is resistance, and that's the answer to this question. So you guys know what each of those measures? All right, get the points. A closed circuit. It's a circuit in which charge. Yeah, can flow. Like the question 2 questions ago. It's basically the same question. Right? If it's closed, the current can flow all the way around from, say, the anode to the cathode to the battery. Whatnot. If you open the switch, everything turns off.
Oh, man.
All right. When two light bulbs are connected in series, one after another, is it the same current that always flows through each bulb? Or is the current proportional to the resistance? In series, which way? How do you do that? Oh, one winner. One winner. So, here, okay, all right. Let's go draw this out here. Draw this out. So, guys, it said series. So, here, I'll draw a couple of circuits. I'll do a series and a parallel. And I want you guys to tell me which is which here. Let's get a battery going. Let's do this circuit versus this circuit. Guys, what is this? Series or parallel? Series. What is this one?
Parallel.
Parallel. Okay. So the question you guys just got had something to do with series. See, there's just a one-way street. Okay. And all the current has to flow there. Okay. I'll put some numbers on it. Let's call this 12 volts. Let's call this guy about 3 ohms, and we'll make this guy. Let's go 1 ohm. Let's go 1 ohm. How about that? Okay. 3 ohms and 1 ohm. What's the total resistance? 4 ohms. So I'll say resistance total is 4 ohms. So we got that. Okay. And then let's do Ohm's law. I equals V over R. So you guys got how many volts? 12. Acting on how many ohms? 4. So what's the current? 3 amps. Okay, guys, 3 amps leave the battery. You guys see 3 amps leave the battery? How many amps go through this resistor? All 3 amps. How many amps go through this resistor? All 3 amps. So guys, it's 3 amps everywhere. Anytime you have a series setup, the current's the same everywhere. And here's my Kirchhoff rules. Kirchhoff rules. Guys, it's this right here. This was the question you guys just got. For series, the current's always the same through the resistors, even if they're different resistances. The current's the same in series. Okay, now, parallel that changes, but let's see what we got next here. The symbol used to represent resistance in a schematic diagram. Yeah, zigzag. Zigzag. There's your resistor. I don't think one straight line was anything. Zigzag. Right, resistors put into series. What happens to the overall resistance? Yeah, larger resistance. In fact, that's exactly what we just did right here. Okay. You guys remember these resistors in series? I got 3 ohms here, 1 ohm here. What was the total resistance? 4 ohms. You just add them up, don't you? Okay, 3 plus 1. Okay, so now as long as you're working in series, the more resistors you add, the resistance increases. Okay. I'll switch over parallel. Parallel might be a different story, but in series, is that okay? You just add them up. All right. Oh, winning. When here, parallel with each other, what happens to the overall resistance? Parallel. Yeah, the resistance does decrease. Okay, let's run some numbers on that because I do have a parallel setup here. Yeah, split this favorably. How about let's call this guy. How about let's try 3 ohms here and 6 ohms here, and we'll see what happens. Okay, so 6 and 3. Okay. How would you find the total resistance? Could be whatever what.
Something or some.
Yeah, product over sum. There you go. Product over sum. Okay. So is that like 18 over 9? And guys, what does that come out to? 2 ohms. Oh. So guys, if you look at the total resistance compared to each individual resistor, what happened with the total? It got less, didn't it? Yeah, guys, the total resistance is less than any of the individuals. Oh, but hey, doesn't that align with the story of like 2 guys painting events? Takes this guy 3 hours, this guy 6 hours, they make a 2-man team. Now they can do the entire job in 2 hours because it's the same math working in parallel. resistors in parallel. Right, so the total resistance would decrease. More lamps are put into series, the overall current does what? Would decrease. All right, so most you got that, but what is that? Okay, so we're back to series. We're thinking about series. Okay. Guys, as you put more and more resistors in series, isn't this resistance increasing, increasing, increasing? So now maybe this 4 could go 5, 6, 7, 8, 9, 10, or it keeps get bigger, which means the overall current, I is current, okay, does what? Get smaller, right? Because you're dividing by a bigger number. Right? This I, of course, is current. You guys good so far? Anybody got any questions? You guys have questions? Let me know. More lamps put into parallel the overall current. Does increase the overall current, say from the battery, there's battery. Okay. Try to convince you guys that's also true. Okay. Here, so we're talking about parallel. Guys, what if I added on another resistor here? Oh, hey, isn't that like getting a third friend to help you paint the fence? Right, which it takes even less time to overall, right? Right. Or in case of resistor math, if I add on any more resistance in parallel, the total resistance would have to come out to less than 2 ohms in that case. Yeah. Okay, how about right. And I can show you guys this too with these. Okay. All right. So like I have one bulb connected to the battery. Okay, pretty bright, right? Pretty bright. Okay. If I do 3 in parallel, right? Now each individual bulb is as bright as the original one was. Okay. Guys, if I attach a fourth one, doesn't that one also light up super bright and these stay as bright as they were? Okay. So from the battery's point of view, every time I add on another bulb in parallel, it has to also feed, or sorry, another bulb in parallel in it. Okay. It has to also feed that bulb. So there's a few perspectives on that answer. Right, women. Compared to the resistance of 2 resistors in series, the same 2 resistors in parallel. Yeah, would be less resistance, would be less. Right? For example, if I had 2 and 2 here, 2 ohms, 2 ohms, what's 2 plus 2? 4, right? But what if I had 2 and 2 in parallel? What would the overall resistance be? Would only be 1, right? Right? Because 2 times 2 is 4, 2 plus 2 is 4, so that would come out to 1. When one light bulb in a series circuit burns out, that contains several bulbs, what happens? None of the other bulbs will light up. Let me draw this out and convince you guys that's true. It did say series. Okay. You guys ever seen like a string of Christmas lights? Okay. There are different ways you can manufacture a string of Christmas lights. One is that you can put all of the Christmas lights in series. Okay. And then, guys, if this one right here burns out, doesn't that open the circuit and then no current can flow? And then they all turn off. Okay. But another way you can manufacture a string of Christmas lights is to put them all in parallel. Now, let's say this one here burns out, then what happens to the other ones? Yeah, the current still flows through all the other ones, and in fact, they're just as bright as they were before. That's for parallel. Okay. So what's going on in series? What's going on in parallel? Two different things. Okay.
Why does it, the last one not get any current? To become the no resistance?
Oh, this one right here? Yeah, because the current can still flow around through that. There's still a path that goes through this one.
What's wrong? They have a resistor in it, the last one?
Yeah. Okay. Yeah, I know what you're talking about. So you're talking about one that looked like this. Okay. Like that one? Okay. Okay, so here, I'm gonna call this how about 1 ohm, 1 ohm, 1 ohm, and 1 ohm. Let's make this up, okay? Okay, so like that. All right, now from the point of view of the current going through the circuit, like when it hits this junction right here, this junction, it sees like 2 ohms of resistance here and it sees 0 resistance here. So 100% of the current goes along this line. Okay, and these are not even part of the circuit. So your entire circuit is right here. And now those two would be in series. So the total resistance is 2 ohms. Okay. And these other two don't even matter. I could have made these like 500 ohms and it wouldn't matter at all. Okay. But up here, there is no path of no resistance. Okay. This would open the circuit here. So yeah, if this was like a wire, this would not turn on. Okay. But none of these others would either. Okay. But guys, what if you do this? What if you put a wire right here? What if I put a wire right here? What happens to all these lights? Yeah, guys, these all turn off. All these lights turn off because now all the current goes through that short, and none of these lights light up at all. Okay. Versus if one burns out and it just opens the circuit at that point, then it's like just closing the road, and then the current still flows through all the other ones. Yeah, that's the difference. All right. One bulb in a parallel circuit burns out. What happens to the other bulbs? Same as before. Okay. That's what I was just drawing right here. Okay. So if you have all these in parallel and then one burns out, okay, then yeah, there's still a path of electricity through the other one, so that's okay. So yeah, if you ever buy a string of Christmas lights and you have like a dead bulb or something, but it's a single dead bulb, but all the other ones are lit up, that's because they're strung up in parallel like that. All right. In a simple parallel circuit, is the current through each branch always the same, or is the voltage drop across each branch always the same? Only one of those is true. Which one? Yeah, it would be the voltage is always the same through each branch. Okay. Not necessarily the current. It could be the current if all the resistors are the same, but if they're not, the only one that has to be true is the voltage. Okay. And as an example, here I'll go back to. Here, you guys remember this right here? These three are all in parallel, aren't they? All in parallel. Okay. Well, let's look at this table because the answer is really in this table. Okay. So I have a 24-volt battery. 24-volt battery. Okay. Now, oh look, all 24 volts go across every single resistor. Okay. And if you like the waterfall model, the cliff model, isn't it true if you pump up 24 meters, every single waterfall has a height drop of also 24 meters? Right? That's true? Okay. Okay, so that's all thinking in terms of voltage or elevation on the analogy. Okay. Now, if you want to think in terms of current, how much current goes through each resistor depends on the resistance. So I did give you guys, in this case, different resistors. So 12 ohms, and 6 ohms. Okay. Guys, where do you think, I'm going to cover up this column. Where do you think most of the current or more of the current would travel? Does more current travel through 6 ohms or 12 ohms? Here, I'll ask guys, I'll ask that a different way. If you're driving around town and you see this road has 6 stoplights and this road has 12 stoplights, would you rather drive through 6 stoplights or 12 stoplights?
Obviously, the 12 stoplight.
You're graduating high school. Yeah, let's go through 6. Yeah, 6. Okay.
Hello,
So,
Super Senior.
all right, so if you run Ohm's law, do you guys see that more current 4 amps go through the 6 ohms, but only 2 amps go through the 12 ohms? more current goes through the path of least resistance. Ah, yeah. Okay. And then if you wanted to apply this page to it, that would be this one right here. More current goes through the branch with less resistance. Ah, yeah. Yeah. Getting that. All right. So okay, simple parallel circuit. Is the current through each resistor inversely proportional to the resistance? Is the current divided at each branch? Is the current, or sorry, is the voltage at each branch the same? Or all the above? Parallel circuit.
Oh.
Yeah, all the above. All the above. Right, those are all true statements for a parallel circuit. Right, you guys get on all those. Get on all those. All right. Fuses and circuit breakers. Yeah, all the above. All the above. All right. I think we only briefly talked about this once. Never. So, it's what if you have, what if you take, here, you have some appliance and you plug this into the wall outlet where there's 120 volts. Okay, I don't think it's technical. I think these lines actually refer to usually a battery, but let's ignore that. Okay, let's say I plug this in. Okay. So I'm getting 120 volts, and I got some appliance has some resistance, whatever. And let's say, maybe I accidentally dropped my twister in the bathtub. Oops. And so now it shorts it out, and now we got all this like flowing. That would be dangerous, right? Yeah, you definitely don't do that because well, uh, won't live to see another day. Unless maybe there's a fuse thrown in the mix. You guys remember that fuse right there? Looks like that. Okay, so then burn that fuse, and that would open the circuit and stop the electricity from flowing, which would be what you need in that case. All right. Ooh, lots of points. Oh yeah. A short circuit occurs when yeah, the positive is connected directly to the negative. Right. So, right, like this battery here, this paper clip. Right now, technically, this paper clip is insulated by something, but I'm going to ignore that. If this was all metal and I touched the leads like that, what would happen to the paper clip? What would it feel like? Very hot. Again, the only reason it's not is this was like plastic coated, but if it wasn't, yeah, this would be getting real hot real fast. Okay, I could probably start a fire with it if I wanted to. Okay, but the battery would drain really quickly. So instead of lasting for like months or years, it would, yeah, it would drain pretty fast. Oh yeah, would be a paperweight. Ah, getting points. Yeah. Two lamps, one with a thick filament, one with a thin filament, connected in series. The current is what? Oh, ooh. All right, so let's definitely go over this. Guys, the current's the same everywhere. Actually, if you think about it, you guys did see an identical question earlier. Let me convince you guys that's true. Let's go back to this. You guys remember these notes from earlier? Okay. Okay, so, guys, the thick filament, thin filament. Which one would be 1 ohm and which one's 3 ohms? Like, which one's 1 ohm, the thick or the thin filament? Let's go. Guys, if you have a little skinny wire, does it have a lot of resistance versus a really fat wire has less resistance? Is that okay?
Yeah.
Okay. Yeah, you guys remember your dose cylinders from yesterday? Okay, guys, here it goes like resistance equals resistivity times length divided by cross-sectional areas. So the larger the cross-sectional area, the less the resistance. So I think this one here, this one of them has the thick filament. Thick filament. You can see a cross section of it. Maybe it will look like this if it was your Go cylinder. Versus 3 ohms, that's a lot of resistance. So if you made a cylinder out of that, maybe it's a little skinny wire, a little skinny. Okay. I see this? Okay. But if they're connected in series, isn't it the same current that goes through them both? And if I use these numbers from earlier, it's 3 amps everywhere. It's always 3 amps. Now you get different voltage drops, but the current's the same. Current's the same everywhere. Two lamps, thick filament, thin filament, connected in series, just like before. The voltage drop is greater across the lamp with the voltage. Yeah, the thin filament, because, guys, the thin filament has what resistance? More or less resistance? Yeah, more resistance. Guys, the thin filament is more resistance. Okay, here, I'll back this up with the formula too. Okay, so I have 12 volts here. You guys see this 12-volt battery? Now, it's going to drop some volts here and some volts here, but the total drop has to also add up to 12 because that would complete Kirchhoff's loop rule. Okay, isn't that the loop rule right there? Okay, but what is each individual voltage drop? Well, that's going to be proportional to each resistor. You guys see this expression right here? Actually, let's run the numbers for this one and this example. So let's run the numbers. Okay. So this one right here, 3 ohms. Guys, what's 3 ohms divided by 3 plus 1 would be 4? Guys, 3 over 4, that's like 3/4. And the battery, I said, was 12 volts. Guys, what's 3/4 of 12? 3/4 of 12? 9 volts. Okay. And then from the perspective of the other one, I have 1 over 1 plus 3.
Yeah.
That'd be like a quarter. Guys, what's a quarter of 12? 3 volts. Okay. So what I'm saying is we're going to pump up 12 volts here, and we're going to drop 9 volts and then drop 3 volts. So like if we make a waterfall model, this could, say, do a waterfall model over here. Going to step down, and then step down again. Could look something like this. Okay. Okay, so I pump up 12 volts. You guys see this battery going to pump up 12 volts right here. Okay. And then we've got the stream of water. It's just one-way street because it's all in series. Okay, but ooh, a pretty big waterfall. That's like 9 meters tall. Here's your 9 meters or 9 volts. Okay. And then we have a shorter waterfall that's only like 3 volts tall. You guys see, and then back to the pump and round it goes. Okay. Just like that. Right. Two lamps, thick filament, thin filament, connected in parallel. The voltage is greater across the lamp with the same voltage, which is actually a question you guys also saw earlier today. Guys, it's this one right here. Anytime you have resistors in parallel, it's always the same voltage drop, even if they're different resistors. Guys, is that true? What if resistor A is like 5 ohms, and resistor B is like 500 ohms? Ah! Would the voltage drop still be the same across both? Yeah, it always is, right? Now, what's different is the current that flows through. Because where is more current going to flow? Through 5 ohms or through 500 ohms? How about 5? Yeah, definitely 5. Right. Almost all the current's going to go through 5 ohms. Now, a tiny bit of current would go through 500, but hardly any at all. Okay. And actually, what I just talked about is this formula right here. Here. So if I said like 500 ohms could be resistor B, but then through branch A, that's what it would be directly proportional to. So you do 500 over 505, and that would represent the proportion of the current that goes through the other branch. Okay. Right? So more current flows through the path of least resistance, but the voltage drop is always the same for a parallel. Oh, and that's what else I wanted to show you guys was, you guys remember these in parallel. You guys remember the voltage column? It's the same number all the way down. You guys got on voltage drop is the same for parallel? Okay. But only for parallel. All right. Boom. Two lamps, thick filament, thin filament, connected in parallel. The current is larger. Where does more current flow? You're driving out on the interstate. Would you rather drive on a 1-lane interstate or a 10-lane interstate? Yeah, let's go 10 lanes. Okay. Yeah, so more current flows through the path of least resistance. If it gets to, like split because of parallel. Right? And least resistance would be the thicker filament, the greater cross-sectional area. Okay? Kind of combined with your lab yesterday. Guys, good. Good. All right. 70-watt bulb connected to 12-volt car battery. When another 70-watt bulb is connected in parallel, the battery's output energy. Okay. Guys, we got to feed the first bulb and now also the second bulb in parallel, like rungs of a ladder. Rungs of a ladder. Okay, yeah, it'd have to double. Here, give you guys a visual here. Yeah, paper. Okay. So if I have a single bulb, ooh, look up bright, single bulb. Okay. Now let's do three in parallel. You guys see three in parallel? Ooh, every individual bulb is as bright as the one was by itself. Okay, okay, so from the point of view of the battery, like here's the battery. Turn it that way, actually. There you go. There's the battery. Okay, here's one bulb. I have to feed that bulb. Right, so there's so much current that goes through. I have current. Okay. But if I put on another one in parallel, now isn't it the same current has to flow through that one? So if it was like 1 amp before, now it's 1 amp, and also another 1 amp. So now we're up to 2 amps from the battery. If I do another one, also in parallel, now I have to supply all those. Okay? And they're each staying as bright as they were before. Okay, so now I've effectively tripled the total current leaving from the battery. Okay. Boom. All right. There's other ways you can back that with math. Ohm's law, Joule's law. The total resistance of 9 ohms and 10 ohms in series. What's 9 and 10 in series? Yeah, 19, because 9 plus 10. Okay. In series, you can just add them up. That's okay. Series, add them up. 9 plus 10 is 19. 9 ohms and, or sorry, 10 ohms and 10 ohms in parallel. Ooh, parallel. What is 10 and 10 in parallel? Okay, 5 ohms. Let me show you guys work this out. Okay. So we're doing 10 and 10 in parallel. So here I got 10 ohms, and here I got 10 ohms. Okay. Guys, isn't the total resistance? I can do product over sum, right? That's one way to do it. So let's do 10 times 10 over 10 plus 10. This is ohms. Is that like 100 over 20 ohms? Is 5 ohms. 5 ohms. Okay, you guys go to 5 ohms, right? Or hey, what if you change the story a little bit? What if it was 10 hours to paint a fence and your friend 10 hours to paint a fence? You make a two-man team. Can you paint the whole fence together in 5 hours? It's the same math. Current through two identical light bulbs is 1 amp. The total voltage is 140 volts. What's the resistance of a single bulb? Somebody, one winner, check out. All right, so I just been solving. Okay. Guys, these are two bulbs in series. Two bulbs in series. Okay. I'll say I don't know what the resistance is yet. We're solving for that. So I'll just call it R. And they did say identical. So R and R. Okay. Which means that the total resistance would be 2R, wouldn't it? 2R? Okay. Now here's Ohm's law. I'll label this one Ohm's law. Okay. And we have 140 volts takes the place of the voltage. 1 amp takes the place of the current. Okay. And in place of the overall resistance, I'll put 2R, where this R actually represents an individual resistor. Okay. Okay. So then just divide by 2, get 70 ohms. There you go. That's it. Okay. Or if you work back from the answer, if you had 70 here, 70 here, that makes 140 ohms. 140 volts on 140 ohms brings you back to 1 amp. In order to make a flashlight bulb light up, all you need to do is run a wire from the positive terminal of the battery to the center of the bulb space. Will that turn the lamp on? You guys are right. Yeah, it would not, because you need a closed circuit. Okay. Here, I'll draw it up just in case you see that picture too. It's like you have a battery, split positive in here. Okay, and you run to the bulb's base. Okay, it's got this filament here. Okay. So that's all you do. The bulb doesn't turn on. Okay. To turn it on, you need to force the current to flow through the filament and then create a closed circuit by bringing another wire back to the other lead of the battery. Yeah. Yeah.
For Mr. Jenkins. Oh, thank you.
Light bulbs connected in series, they all carry the same current regardless of their resistances. True. Yeah. All right, so you have seen that a few times. Okay, as long as they're in series, it's a one-way street. All the cars have to travel on one street. All the current has to travel in amps. It's the same current in series. In a series circuit, the total voltage drop across a series of resistors is the sum of voltage drop across each individual resistor. Yeah, that reminds me a lot of Kirchhoff's loop rule. You guys remember this loop rule right here? Right? Or those waterfall models could also be a good visual. Yeah, that is true. That's like the loop rule. In a parallel circuit, current in each branch is the same. In parallel? Okay, false. Let's see. Let's go back to this. Okay, so guys, here's a basic parallel circuit. Now there is something that's the same across the guys. What has to be the same across both of these resistors? Not the current.
Voltage.
Yeah, the voltage. Right? The voltage has to be the same, even if they're different resistances. We'll say. But the current's going to split, and the current is probably going to be different. The only way for the current to be the same is if these resistors themselves were equal to each other. But in general, that's not going to be the case. Okay? So yeah, more current turns out goes through the path of least resistance, and the current then would be different. A schematic diagram is a simplified, blocked out picture of a circuit in which parts of the circuit are represented by symbols. Yeah, true. Schematic diagram we've been drawing. When resistors are arranged in parallel, their overall resistance is less than that of the smallest resistor.
Wow.
That is true. Guys, isn't the math the same as
teaming up to paint a fence or doing any kind of teamwork, really. As if it takes you so many hours and your friend so many hours and your third friend so many hours, when you get together, isn't it true? Whoever was the fastest has the smallest time to paint the fence by themselves. If they're working with their friends, the time has to go down, doesn't it? Right? Same thing with resistors in parallel. Right? Once you add more and more resistors in parallel, even if each individual resistance is really big, the overall resistance has to decrease in parallel. In order to prevent overloading in a circuit, fuses are inserted. That sound right? Yeah, sounds true. 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 All right, you guys ready for the win? Ready for the win? Who's gonna win? Who's gonna win? A fuse is usually inserted in parallels. Does that sound right? Which way is it? Where did I draw a fuse before? Here it is. There you go. Yeah, you guys all got it anyway. Right. Because you said, no, that wouldn't go in parallel. That has to go in series. Okay. So, like, if I put it in parallel, it would completely defeat the purpose. And I'll show that to you guys. Okay. Like, what if I had this? What if I put the fuse right here, and then some appliance over here? Okay. Guys, if this fuse burns out, does the current still flow? Yeah, current still flows. Right. So it doesn't really do anything. So yeah, this would not be what you want. Okay. This is how you arrange the fuse. This is the fuse right here. All right, let's find out who won Kahoot with the bronze, Dara, silver, Anna, and the gold, Sean Combs.